Hi everybody, I hope this video finds you well. Today we're going to be discussing a mathematical way to measure the strength of the correlation between two quantitative variables. This is going to be a follow-up to our previous video where we introduced sort of the three things that we want to measure about correlation, namely the direction, the form, and the strength. We sort of talked about how form and direction are often things that we can sort of do visually, whereas strength is something that we want a more formal way, a more mathematical way of measuring. And to do that, we're going to introduce what's called the correlation coefficient. So let's begin by giving a definition. So the correlation coefficient denoted R measures the strength of the linear correlation between two quantitative variables. Okay. So there's a couple things that I want to call your attention to in this definition. The first is a little bit of notation. Whenever we talk about correlation coefficient, we're always going to be using the letter R. So if you ever see R referenced in statistics, you know that that's talking about the correlation coefficient. The correlation coefficient is going to be our measure of strength, but it measures a very specific type of correlation. You have to remember that the correlation coefficient is measuring the strength of the linear correlation. Now, linear correlation is not the only type of correlation out there. So while this is good for our class because it's going to be the type of correlation that we mostly focus on, you do want to remember that the correlation coefficient is limited to measuring linear correlation. You'll also notice that, again, we are talking about pairs of quantitative variables. So we're going to be continuing, just like we did in our previous lecture, always focusing on understanding the relationship between two quantitative variables. All right. Now, in this video, we're going to mostly focus on talking about some properties of the correlation coefficient, using the correlation coefficient to understand when there's a relationship between variables, and doing an example of all of those sort of pieces. For computing the correlation coefficient, that's a pretty messy, sort of tedious computation. And for our class, we're going to be using our calculator to actually take care of that computation. There's a separate video on our sort of YouTube channel that you can watch to see how to use your TI calculator to actually calculate the correlation coefficient along with some other things that are useful when doing correlation and regression. I would recommend watching that video so that you are comfortable using your calculator to calculate the correlation coefficient as well as those other things. At the end of this lecture, there will be an example where we will run through using the correlation coefficient, and it probably would be useful to be able to follow along with that example and know how to use your calculator to calculate that correlation coefficient. So if you haven't watched that calculator video, I would recommend going ahead and doing that and then continuing on with this one. For now, in this video, though, we're going to talk about some properties of the correlation coefficient. So the first property of the correlation coefficient is that anytime you calculate a correlation coefficient, you are always going to be getting a value between -1 and 1. That means correlation coefficients are never going to be something like 2 or -5 or anything like that. It's always going to land between -1 and 1. This sort of tells us that the correlation coefficient is sort of like a spectrum. So if we imagine like a number line here, if that's -1 and that's 1, and of course right in the middle would be 0. Well, this tells us a couple things here. In this section over here, where you'd be getting positive correlation coefficients, that would be things like 0.2 or 0.5 or 0.8 or something like that. This, if you get a positive R, this implies a positive direction. So while the correlation coefficient is there as a measure of strength, the sign of the correlation coefficient, whether or not it's positive or negative, actually also relates to the direction. The same would be true over here in this section when you get a negative R. So you get something like -0.5, -0.8, something like that. That implies a negative direction. Okay? So that's very sort of important. You just got to remember that the sign that you're seeing of your correlation coefficient, negative or positive, corresponds directly to the direction. All right, so how does this actually help us measure strength? Well, it's sort of interesting, right? The two ends of this number line are going to be where we're seeing strong correlation. So if you get values down here close to +1, that's going to be strong positive correlation. Whereas if you get things close to -1, this is strong negative correlation. If you're sort of near the middle in here, that is where we would say you have weak correlation. Now, of course, you might say, well, okay, what happens if we land in here, in sort of the middle areas? Well, of course, we could just say that that's medium, right? It's not weak, it's not strong, it's just medium. In a little bit, we'll talk about exactly how to assess what counts as strong enough or what counts as too weak. But just be aware now, the closer you are to -1 or 1, the stronger you are. And the closer you are to 0, the weaker the correlation is. What happens if you show up exactly at those sort of endpoints? Well, just as a little note here, if we ever see r equals ±1, this indicates sort of what we call perfect linear correlation. And this doesn't really happen too much in real life, but what this would mean is that if you ever got a correlation value of exactly +1 or exactly -1, that would mean that on the corresponding sort of scatter plot, the points would fall on an exact line. In other words, you could draw a straight line through all the points. Doesn't really happen in real life with real life data, but that is what the sort of two extremes of our -1 to 1 really correspond to. The other sort of note that I want to call your attention to is just a reminder about the limitations of the correlation coefficient. When you get a correlation value near 0, so you're somewhere right in here, what you need to remember is that means there is no linear correlation. So the reason I'm calling attention to that is a reminder that the correlation coefficient is measuring linear correlation. So when you get an R value that's very close to 0, that could mean that there's no relationship whatsoever, or it could mean that the relationship is non-linear. And unfortunately, based on the correlation coefficient, you're not able to make the decision between those two. That's why we need both a scatter plot and the correlation coefficient. If you draw a scatter plot and you see no pattern to the points and the R value is really close to 0, that tells you there's no relationship. If you draw a scatter plot and you see a strong U shape or an S shape or something like that, you might still get an R that's basically 0, but you would realize from the picture, oh, there's a non-linear relationship. So just remember, when that R is close to 0, that just means there's no linear correlation. All right, as you can probably tell, that's a lot to say about that first property. So property 1 is really important. So we'll put some little stars around that. The other properties we're going to talk about, just a couple other ones real quick, are equally sort of interesting, but maybe not as essential for using the correlation coefficient. So the second one we're going to talk about is that R is unitless. All this means is that changing the units of the explanatory and response do not change R. So all this basically means is if you're calculating, say, a relationship that involves the explanatory variable of height, if you change how you measure somebody's height, maybe you switch from inches to centimeters or inches to feet or something like that, just by changing those units, you won't change the R value. And that should make sense. If R is really doing what we want it to do, which is measuring the correlation, measuring the pattern, it shouldn't matter how you decide to measure your variables. It won't matter the units. And that's exactly what the second property is saying. The third property, which is a little weird, is that R is symmetric, which is that saying that if switching the explanatory and response will not change R. Now this is very unique because this is sort of like one of those moments that's a difference between mathematics and statistics. In mathematics, calculating the R value, if you change which variable counts as explanatory and which counts as response, the R value will not change. Now, statistically, we spend a lot of time making sure that we know which is explanatory and which is response, because that determines how we would interpret our information, how we would make predictions, etc. But mathematically, if you accidentally switch the explanatory and response, the R value will remain the same. And that's just called R being symmetric. Finally, R is a measure, so we should briefly mention resistance. R is not resistant. If you remember, we introduced resistance way, way back when we first talked about like mean and median. All this basically is saying is that R is based on mean and standard deviation. So extreme values will impact R significantly. So if you guys remember back to our discussion of like mean and median and things like that, we talked about this concept of resistance. Some statistical measures are resistant, meaning that they are not greatly impacted by extreme values, and other measures are not resistant, which means that they are impacted by extreme values. The correlation coefficient, behind the scenes, sort of what the calculator is doing for you, is a computation based on mean and standard deviation. And that basically means that the correlation coefficient is not resistant. So if you have extreme values, you have data points that don't fit the general pattern of your data, those data points can greatly impact the correlation coefficient. So we got to be very careful about using the correlation coefficient when we have those sort of extreme values or those outliers. All right, so these are some important properties. Again, most of the time we'll basically just need to think about property number 1 here. That is the really, really sort of crucial one. But 2, 3, and 4 are also things to just sort of keep in the back of your head about what this correlation coefficient really is. Now, the next thing we need to sort of discuss is how do we actually use this correlation coefficient? We know things close to -1 or close to +1 are considered strong, and things close to 0 are considered weak. But what about that sort of middle area here? So now we're going to talk about actually understanding and interpreting that correlation coefficient. So let's go ahead and talk about how we're going to do that. So we're going to discuss how to use R, use that correlation coefficient, to decide if there's evidence for a correlation. To do this, we're going to need to make use of a statistical table. So to do this, we will use table E. Now, normally we would hand that table out, but as you guys know, right, you have a copy of all the statistical tables that you'll need for this class on your course website. So you'll want to take a look on your course website for this table E. So this is on course site here. All right. What does table E look like? Well, let's just take a moment and take a quick glance at what it actually looks like. So table E looks like this. You'll notice that it mentions that this is talking about critical values of the correlation R. So when you're looking at this, we'll talk about how you actually read this table, and then we'll come back to this in just a moment. So when you go on to table E, to use table E, you need to know one thing: the sample size. So table E is all based on knowing how big of a data set you have, the sample size n. Once you know that sample size of n, the way you read table E is you read table E by following your n value, and then you'll be reading that across. You'll go to the column 0.025, read that down, and you'll find where those intersect. And they intersect at a value that we call the critical value. So when you go to read table E, you'll look up how many data points you have, your sample size. You'll find that in that first column. Then you'll go across to the column that says 0.025, and you will follow that down until you find the intersection. And that'll yield something called the critical value. So what is the critical value? Well, the critical value is basically what counts as strong enough. So if our R value is larger, and we have to do this in absolute value because sometimes the R value might be negative. If the R value in absolute value is greater than the critical value, what this means is that we do have enough evidence for a correlation. If the absolute value of R is less than the critical value, so if your correlation coefficient in size is less than your critical value, this means there's not enough evidence for a correlation. Okay. Now, I know that this is a lot of sort of information and we might not be exactly sure what table E is really doing. So just keep in mind that basically table E yields something called the critical value. and then we compare our correlation coefficient against that critical value. If our correlation coefficient in absolute value is larger than the critical value, then that tells us there actually is enough evidence for a correlation. In other words, that the pattern we're seeing in the data is strong enough to really be considered a true pattern. Whereas if the absolute value of R is less than the critical value, then we determine that there's not enough evidence for a correlation. In other words, while we might see a slight pattern in the data, it really isn't enough to say that that's a true pattern or a true relationship between our variables. All right, we're going to do an example in just a moment of all this, but let's take one look at what table E really looks like. So you'll notice that on my table E, I've already sort of highlighted that 0.025 column. The table E that we have, that we're using for this class is a little overkill. You don't need any of the other columns. We're only going to be using that 0.025. So on your copy, you might as well go ahead and highlight that or something like that. You'll notice over here in that first column is that n value. So you'll pick out how many data points you have. Say we have an example where we might have 7 data points. And then we would take that 7, we'd follow that across right here, and this guy right there would be our critical value. So we can see our critical value would be 0.7545. What that means is that if we only have 7 data points, we have to have a correlation coefficient that is greater than 0.7545 in absolute value to really count as a pattern. So what is this table overall sort of doing? Well, you'll notice that this column here gets smaller and smaller as we have more and more data. And this should make sense. In other words, what we're saying is that if we have a lot of data, we don't need as strong of a pattern because we have a lot of data to support it. But if we have very little data, like up here, we need an incredibly strong pattern before we're willing to believe that it's a pattern. That's really what this table is saying. Last question you might ask yourself is, why do we only use this 0.025? Well, that's basically out of convenience. It's sort of like another statistical standard. Much later on in this class, when we start talking about hypothesis testing and p-values, we can come back and discuss how you could use these other values here and here. But for now, we're always just going to use this 0.025. All right, so that's a lot of information. Let's go ahead and take a look at an example putting all this stuff together. So in this example, we're going to suppose you're interested in studying the relationship between the budget and revenue for blockbuster films. So to do this, what you do is you collect the data about 12 recent blockbuster films, you record their budget in millions of dollars, and their revenue also in millions of dollars. So we get the following data here. Now again, do remember how to sort of read this stuff, right? This first guy here would indicate that whatever that first film was had a budget of $400 million and a revenue of $860 million. Now, actually, interestingly enough, this data is adapted from real data. This guy right here is actually Avengers Endgame, which had the overall sort of highest, one of the highest sort of domestic revenues of all time. That's why we're sort of seeing those really extreme values. It also had the highest budget of all time. Just pointing out some other ones, you'll notice that some of these movies maybe were not as successful as others. We actually have one of the most famous flops in cinema history in this data set right down here. You'll notice our 11th data point was a film that had a budget of $260 million, but only brought in $70 million in revenue. This guy right here is one of the rare flops for Disney. This was John Carter. Which goes down in history as probably one of the most legendary failures in cinema history. So there's our data set. Each of these represents sort of the budget and revenue, with all these values representing millions of dollars. All right, so what are we trying to do with this? Well, as always, we're going to begin by trying to identify the explanatory and response. Then we're going to go ahead and draw a scatter plot. And then as sort of the new piece, we're going to calculate the correlation coefficient, meaning that we're going to put this stuff into our calculator and actually go ahead and get that correlation coefficient. And then we're going to decide if there's enough evidence for a correlation. So a couple things to do with this. So to begin with, we got to talk about explanatory and response. Again, that should be pretty clear here, right? It doesn't really make a lot of sense to say that your revenue would determine your budget, because of course your budget should sort of come first. So the natural way is to think that your budget should help explain your revenue. So that means that the budget here is going to be explanatory, and the revenue is going to be response. Now, if you've watched the video about using the calculator to calculate correlation coefficient, you'll know that there's another reason that it's important to get explanatory and response. You'll know that when we go to type this data in, you'll want to put the explanatory into L1 and the response into L2. And I would recommend, if you've watched that calculator video, it's probably not a bad idea to just go ahead, pause this video right now, and type this data in so that you can sort of follow along. All right, so we've identified the explanatory and response. Let's go ahead and draw our scatter plot. So for the scatter plot here, remember what we're going to need is just a nice sort of quarter of a coordinate axis here. Remember that the explanatory, which is going to be your budget in millions of dollars, is going to go down here. Let's take a quick look at the budgets. Looks like the largest budget we had was 400, and the smallest budget was 260 million. So we'll need an axis that sort of shows that. I'll just go ahead and start mine at 260 and go by 20s. There's 280, 300, 320, 340, 360, 380, and 400. Again, we can put in our little squiggly line in here to indicate that all those values from 0 up to 260 million have been condensed. All right, for revenue, let's go ahead and be careful here. The largest revenue actually was this guy here with 940 million, and the lowest was about 70 million. So that's a pretty wide range. So we'll need a pretty large, probably a pretty large scale here. So let's go ahead and start this guy at 0, and then we'll just go by hundreds. So that'll be 100, that'll be 200, that'll be 300, that'll be 400, that'll be 500, 600, 700, 800. We'll extend the axis just a little bit, and that guy up there will be 900. Looks like we would need to go one more though, and call that 1,000 or 1 billion, I guess, actually overall, because it'd be 1,000 million. And this, of course, is the response variable, which is revenue in millions of dollars. Now, I know mine is a little bit messy here, so I do apologize. I am just going to go ahead and erase that sort of word scatter plot because I think we all know what we're building here. Okay, so let's go ahead and plot this real quick. Notice that I did not need to use a little squiggly line down here because I actually did start my vertical axis at 0. All right, so my first point is at 400 with a revenue of 860. So we'll just sort of roughly sketch that on. That should be right in there. Then we had 380 and 240. So that looks like it should be somewhere right about in there. Then we had 370 and 460. So that should be maybe somewhere about in there. Then we had 310 and 940. So somewhere way up there. Then we had 300 and 310, so that looks like somewhere right about in there. Then we also had my point looks a little sloppy, I do apologize, we'll just redo that guy. That was 300 and 310, so that looks like somewhere right about there. Then we also had 300 and 200 right there. Then we also had 300 and 680, so somewhere way up there. And we also had 300 and 230, right, which is maybe right about there. Okay, we also had 280 and 520, so that's somewhere up there. We also had 270 and 210, so that's probably somewhere right about there. And then we had 260 and 70, so right in there. And then we also had 260 and 330, so maybe somewhere right in about there. Okay, so sorry if that's a little bit messy there, but just trying to sort of freehand that. So what could we say about this data set? Well, even before we calculate the correlation coefficient, right, if we sort of imagine, it doesn't make a lot of sense to sort of indicate this like that. In other words, we are sort of seeing, generally speaking, a positive pattern, right? We're sort of seeing as we move this way, we're also seeing a general increase that way. Sort of. But there's a lot of scatter, right? We can see that by far the highest revenue actually came from this movie that was sort of low in terms of its budget. And we also had some very high budget movies here and here that didn't really make that much revenue. So we're certainly not seeing a particularly strong pattern in this. But if there is a pattern, we'd probably say that it's positive, not negative. So as we do this, as we calculate the correlation coefficient, we're expecting sort of a positive value, but not a particularly large positive value. So if you've watched the calculator video, you'll know that you want to go ahead and put this in L1 and this in L2. And then you're going to want to run the ln reg ax plus b. And once you do that, you want to record your R value. So I have my value sort of pre-typed in. I'm going to go ahead and calculate that. And when you actually calculate that, you should get an R value of about 0.4214. And notice, as we sort of anticipated, this guy is positive, but not particularly close to 1, which is sort of telling us we're seeing a weak to maybe medium positive correlation here. All right, let's decide then, is this enough evidence to really determine that these things are related, that budget is really impacting the revenue? Well, to do that, we're going to go ahead and use that sort of table E. So let's go look at table E here. And to do that, we need to know the size of our data set. And our data set here is n equals 12. Right? We know that because we could literally go through and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or we could just remember that they told us we had 12 films in our data set. So we have n equals 12, and we'll go back to our table. If you have your table, you can follow along. So we have n equals 12 right here. We have our date, our 0.025 right there. So we're just going to come across to here and go right there. So it looks like our critical value should be that 0.5760. So that is our critical value. So let's go ahead and record that. Our critical value here is going to be 0.5760. So how do we actually put this stuff together? Well, if we compare, we can notice that the absolute value of R, now absolute value is completely unnecessary here because the R value is positive, but just for consistency's sake, we'll write that in. The absolute value of R, well, how does this number here compare to this guy here? Well, you can see that the R value is smaller in this case. So we'd say that the absolute value of R is less than the critical value. So what sort of conclusion do we make then? Well, we would say there's not enough evidence for a correlation. So after all that work, what we've determined is that there's not enough evidence for a correlation. In other words, we are saying that we are not convinced that the budget is really related to the revenue. Now that might seem like sort of a disappointing conclusion. Like we spent all this time to basically find out that these two things are not related. But you also have to remember that sometimes determining that things are not related is also a result in of itself. It's sort of surprising here, and it's pretty interesting that we're basically finding out that for blockbuster films, the budget doesn't really impact the revenue that you expect to pull in. So, in other words, spending tons and tons of more money making a movie is not a guarantee that you're going to make a lot more money. So, sometimes finding that things are not related or not correlated is equally interesting as finding that they are related. In our next video, we'll take another look at another example about this and then talk about what can be done if variables actually are related.